Hello everyone. In today's session, we'll learn how exactly we can add multiple 16-bit numbers which are stored in the memory and then store back the final result into the memory. So before I explain these content, let me just see what exactly is a 16-bit number. So if you see here, value 1 is a label. You can see here there is a term called DCW, which is defined constant word. Okay, and then we have these set of numbers. Okay, when I say that I'll be storing 16-bit numbers in my memory, then I have to always use DCW. If in case I wanted to store 32-bit numbers, I'll have to use the term DCD. And if I want to store 8-bit terms, then I'll have to use that concept of DCB, where DCB is defined constant byte, DCD is defined constant double word. But in our case, it is DCW because we want to store multiple 16-bit values in the memory, and then after that we want to find its sum. I'll show you why exactly I'm calling it 16-bit and what difference it would make if it would be DCD and DCB. Let's just continue here. You can see this is a little different. Always we see at the top, assembler directives like this, wherein read only is written. But here we can see area is same. Okay, area is meant to create a segment in the memory to store whatever data is written below it. Data 2 is a random name. Instead of code here, we have written data here because this line is not any instruction to be executed. It is nothing but just data values are stored here, and here read write access is there because usually we'll just extract few values from the memory. We don't store back any data, but in this particular program, once all final computation is done, here is the label called result, okay, which stores 32-bit value. The final sum of all these values is stored in this particular location. We'll see what exactly it is and how exactly storing in memory happens once I finish explaining all this. Okay, so let's come back here. You already know area gives a specific area in the memory. In order to store all this information, addition is a random name. Code gives information that this section of data is there. It's actual instructions and not just data values as indicated here. And read only because we don't want any modification to be done in this particular information stored in the memory. Entry to indicate that this is where code will start. Start is a label. In our case, we want to add 6 16-bit numbers and their result we want to store back in the memory. That's why it is 6 here. If in case we wanted to add more number of terms, we had to change this value. We are storing R0 as 0, okay, because initially result will be stored in R0 and then finally we want to store it in the memory. Okay, LDR R1 comma equal to value 1. So what this command will do is, value 1 is a label. If we know what exactly is its address, through that we can access all these values. So in order to do that, we are loading the address of this particular label into R1. Okay, and next we have loop, which is nothing but a label. Fine. LDRH. So this will load, but H indicates that 16-bit data should be loaded. Okay, so there are two instructions when it comes to memory operation. One is load, one is store. If you want to copy some data from the memory into the register, we will be using load, while if you want to copy the content of the register into the memory, we'll be using an instruction called store. Okay, we'll see how it works later on. Let me just explain what is happening here. Okay, so R1 basically has an address. If you use a bracket like this, it means the content of R1, whatever address is shown, in that address whatever content is there, okay, that I want it to be copied to R3. Okay, so what this will do is the initial value which is stored, that will be copied to R3, and then I am writing #02. That means now increment the address by 2. Okay, you will understand it more clearly when I show you the memory organization. But what you should know before that is, whenever I am loading a 16-bit data, here incrementation of address will be by 2. And if I am storing 8-bit data, here this also will change. It will be LDRB, and here it will be #1. And if it is 32-bit, it will be LDR and #4. Now, once we have obtained our very first data, okay, we are adding it with R0 content. Initially R0 is 0, so 0 is added and result is stored by, and we are reducing R5 by 1 because R5 is our counter which checks if we have added all the contents. Here we are comparing R5 by 0. If we have added all the content, this condition will be true. But in our case, we have just added the first value, so you will go back to the loop. Okay, so because of this #2 in our previous loop, R1 will be pointing at the second data, and because of which second data is loaded into R3, which gets added with R0, which holds the previous value. Okay, and the result is stored back in R0. This continues until all 6 data are added. Okay, and this condition becomes false. Next, what we are doing is R4, we are loading the address of result. That is, result will be pointing at some memory location. That memory location address is loaded into R4. Then the final result which you obtained by adding all the values, okay, is stored in the address pointed by R4. B jump, this is nothing but an infinite loop. This prevents execution of this particular command. Okay, we want this particular line, make sure the datas are stored in value 1. We don't want this to be executed as an instruction. Okay, now let's see what happens. Okay, so very first thing is R5 is 6, that is 6 numbers we are adding. R0 is stored as 0, and R1 gets the address of value 1. So value 1 is the memory location wherein we are storing all these values, and if you see this, it is nothing but 2C. Okay, so I'll just write that address. Okay, and you can see in what way the values are stored. So our values are 1111, which is stored here in 2 memory location, 0002 in 2 memory location, 0003 in 2 memory location. Why it is so? Because if you consider this particular arrangement, in each location 8-bit data is stored, and ours is a 16-bit data, so it requires 2 memory location. That is because when you say 1 here, if you consider the single element 1 here, okay, it is nothing but 0001. Okay, and same thing here. Okay, so each value here in binary, it is 4-bit. This is hexadecimal value, in binary it is 4-bit. Okay, and because of which 4-bit multiplied by 4 elements, total 16-bit data it is. Okay, because we have specified DCW, it occupies 2 memory location. Okay, and because of which it's a 16-bit data. Now before I think we perform any other operation, I want to show you how it will appear in the memory if in case it was not DCW but DCB or DCD. Okay, so let me just store it as DCD now. So if you can see here, instead of 2 memory location, it occupies 4 memory location. Okay. And one more case would be if it was DCB. Now in this case we have our 1111 value, okay, which is 16-bit only, okay. But if we would take it as something which can be accommodated into an 8-bit value, this is how it would look: 01, 02, 03, 02 and so on, okay. So what is happening here is nothing but based on what we write here. If it is DCB, DCW, DCD, memory allocation depends on that, and also the address increments here depends purely on that, okay. Now we have considered the case wherein we are adding 16-bit data, so let it be DCW only, okay. Let's continue, okay. So let us just see. Okay, so this is where we left executing, okay. What should happen here is nothing but content of R1. See, R1 has an address which is 2C, okay. In 2C, what value is there, okay, and here they have specified LDRH. So half-word or 16-bit data from R1 address, okay. If this is the R1 address and this is the content of that, you can see the bracket here, so that's the content 0100. That should be copied to R3, and the pointer, okay, which was initially pointing at this particular address will now be incremented to next address. Before I continue anything else, you have to focus on one point here. This particular whatever 16-bit data is stored in Little Indian system, where lower whatever data is there or least significant data is there, it is stored in the lower memory address, and higher data which is there, higher significant bytes are there, they are stored in higher memory location. If you will know that if you have seen my other video wherein I show how exactly data is organized in Little and Big Indian system, okay. So let's just continue here, okay. So if you see the next step here, okay, this content should be now stored in R3. Let's see how it happens. Yes, so 0001 is now stored in R3, and then we are adding R0 and R3, okay. So and the result is stored in R0, okay. Then we continue and we subtract R5 by 1, okay. This is because already we have added the first content. Then we are comparing if R5 is 0, which is not the case, so it is not equal, so it will go back into this particular loop. If you notice here, okay, so the value of R1 is supposed to contain the address. Initially it was 2C, okay, now it is 2E. Why is that the case? Because this particular command will make sure whichever address R1 is pointing to, that content is moved to R3. After that, R1 value is updated by 2. It was 2C, so 2C plus 2 in hexadecimal is 2E. Okay, so it will now be pointing at this particular data. So if you continue execution, you can see that the second value is now stored, okay, in our register R3, okay, and we have added that content to R0, our previous value, okay, and the result is stored in R0. We'll see that. Yes. Next, we are subtracting R5 content, comparing, and the loop continues. Then again, we have also updated now R1, as like in the previous case 2e plus 2. Okay, so because of which R1 is currently 30, it will be pointing at this particular value, and the next content is loaded, which is 03, and that content is now added. After addition is done, you will get the answer as 06. So then you continue with subtracting R5, and then the loop repeats. Okay, then again 02 is added, which is the next value shown here. Okay, and the procedure continues. Okay, so now the loop is broken. That is because R5 is finally 0. Okay, and you can see that our current result is A. Let us check if it is correct. 1 plus 2, which is 3, plus 3, 6, 7, 8, 9, 10. And 10 in hexadecimal is A. Okay, so let's just continue. Okay, so what here it is happening is we are loading result labels address into R4, and as you can see here, okay, that value I'm just copying and pasting in the window. Okay, its initial value is 0. Okay, let's see what happens when we are storing the result into here address pointed by R4. So this value is now stored in the location wherever R4 is pointing. Let's see. Now, because already in the memory window I have stored the final result location. Yes, our answer is stored here. Again, you can see because it's Little Indian format, lower data, that is 0A, is stored in the lower memory location, because memory location or memory address increases from left to right. Okay, so that is how you do 16-bit addition. Okay, and if you want, you can take higher numbers. Okay, maybe let's see what answer we get. Now initially we can see our memory location like this because it's usually same. Okay, and then all computations are happening here, and the result is 16665, and that should be stored in the memory location okay. So here we are trying to find the sum of 6 16-bit numbers which are stored in the memory. Okay, and then the result is again stored back in the memory. Okay, yeah, that's all.